gaze at the night sky. Among a myriad of planets, there is one that has captivated our gaze for centuries. Reddish, mysterious, cold. Mars. We call it the Red Planet, send rovers there, dream of colonies. For us, it's a symbol of the future, a new frontier. But what if I told you that Mars isn't our future, but our distant, forgotten past? What if this lifeless desert is our true homeland, and all of us, from the tiniest microbe to humankind, are descendants of Martians? It sounds like the premise of a Hollywood blockbuster, but behind this incredible idea lies a serious scientific hypothesis, backed by facts that will make you look at both Earth and its red neighbor in a whole new way. Let's rewind time. A long, long way back, approximately 4.5 billion years ago, to the very birth of our solar system. During those turbulent times, both Earth and Mars were fiery balls, constantly bombarded by asteroids. Life didn't exist, and couldn't possibly exist. But the planets were cooling down, and this is where things get really interesting. Mars, being roughly half the size of Earth, cooled down significantly faster. This means that the conditions for liquid water to appear, and therefore for life to begin, emerged there hundreds of millions of years earlier than on our planet. Imagine young Mars. This isn't the red, dusty world we know. It's a planet covered in oceans, with a thick atmosphere, clouds, and perhaps even a blue sky. It possessed a powerful magnetic field, which, like an invisible shield, protected its surface from the harmful solar radiation. All the necessary ingredients for life were in place: water, organic molecules brought by comets, and energy sources such as volcanoes and hydrothermal vents on the ocean floor. While Earth was still a hell of lava and steam, Mars could have already been a cradle. Life might have originated there first. But if life originated on Mars, how did it get to Earth? The answer lies in a cosmic catastrophe. Back then, the solar system was like a giant billiard table. Asteroid collisions were commonplace. Imagine an asteroid the size of a large city slamming into a Martian ocean. The colossal impact hurls billions of tons of Martian rock, water, and perhaps even microscopic life that had already emerged in that water into space. These rocks, ejected from Mars's surface, begin a journey lasting many years through the solar system. This process is called panspermia, or more precisely, lithopanspermia. It's the idea that life can travel between planets on rocky arcs. It sounds fantastic, but it's not just a theory. We know it's possible because we've found Martian rocks right here on Earth. To this day, scientists have identified more than 270 meteorites of Martian origin. They arrived here precisely this way. A powerful impact on Mars launched them into space, and after a long journey, they fell onto our planet. The most famous of these visitors is the Allen Hills 84001 meteorite, found in Antarctica in 1984. In 1996, NASA scientists, while examining it under an electron microscope, made a sensational announcement. They discovered structures within it strikingly resembling fossilized, microscopic bacteria. The news swept across the entire world. Could this truly be the first proof of alien life? Heated debates erupted. Skeptics maintained that these structures could have formed from geological processes or been the result of terrestrial contamination. And although there's still no definitive answer, this rock compelled the scientific community to take seriously the notion that Mars might have once harbored life. But can fragile life survive such a journey? First, an explosion of colossal force, then the icy vacuum of space, harsh radiation, and finally, a fiery entry into Earth's atmosphere. It seems there's no chance. But life is far more resilient than we think. On Earth, there are organisms called extremophiles. They live in boiling geysers, in the vents of underwater volcanoes, in hypersaline lakes, and even in the glaciers of Antarctica. One of the champions of survival is the tardigrade, or water bear. This microscopic invertebrate can withstand almost complete dehydration, extreme temperatures from -272 to +150 degrees Celsius, and radiation doses 1,000 times greater than those lethal to humans. Experiments have shown that tardigrades and some types of bacteria can survive in the conditions of outer space. What's more, the inner parts of a large, stony meteorite serve as excellent protection. While the outer layer burns up in the atmosphere, the core remains relatively cool. So, theoretically, microbes hidden in cracks within such a rock could well survive both launch from Mars, a long journey, and landing on Earth. Their journey could have taken thousands or even millions of years, but for bacteria in a state of anabiosis, that is, hibernation, that's no time at all. And then, millions of years later, such an arc falls into the warm, primordial ocean of a young Earth. The Martian microbes awaken and find themselves in ideal conditions for reproduction. They find a new home and begin to evolve. This hypothesis isn't just beautiful, it solves several serious mysteries related to the emergence of life on Earth. The first puzzle involves the speed. In geological terms, life on our planet appeared almost instantly. The oldest rocks that could, in principle, have preserved traces of life already contain these traces. They are approximately 3 8/10 billion years old, and yet, Earth before this period was an utterly inhospitable place. It turns out that the incredibly complex process of transitioning from non-living chemistry to a living cell had very little time. That's like trying to assemble an extremely intricate mechanism in the middle of a hurricane. The Martian origin hypothesis elegantly resolves this problem. Life didn't need to originate on Earth in a rush. It arrived here already pre-made, having undergone the first, most challenging stages of evolution in calmer conditions on early Mars. The second puzzle is a chemical one. Certain catalytic chemical elements are essential for the assembly of life's first molecules, specifically RNA, which is believed to have predated DNA. Two of these are boron and molybdenum. They prevent organic molecules from degrading in water and help them correctly assemble into the right chains. The problem is that, according to geological models, both boron and oxidized molybdenum were extremely scarce on early Earth. However, on early Mars, according to data from the rovers, these elements were in abundant supply. Mars was drier and richer in atmospheric oxygen, which created ideal conditions for the formation of the necessary compounds. This suggests that the chemical factory on Mars was better equipped to kickstart life's production than Earth's. So, let's put all the evidence together. We have Mars, which became habitable hundreds of millions of years before Earth. We have a mechanism for delivering this life to Earth, meteorites, which, as we know for a fact, travel between planets. We have evidence of the incredible resilience of microorganisms, and we have several biochemical and temporal paradoxes concerning life on Earth, which this hypothesis readily explains. The picture that emerges is very compelling. We may not simply be children of Earth, but grandchildren of Mars. But if there was once life on Mars, perhaps even thriving, then what happened to it? Why is it now a cold, dry desert with an atmosphere 100 times thinner than Earth's? The answer to this question is a planetary tragedy that serves as a harsh warning for us too. The key to the puzzle lies in Mars's size. Being a small planet, its core cooled down much faster than Earth's. Earth's liquid metallic core, as it rotates, creates a powerful magnetic field, our magnetosphere. This is our invisible force shield, which deflects streams of charged particles flying from the sun, the so-called solar wind. Roughly 4 billion years ago, Mars's core cooled and hardened. The planetary dynamo stopped, and Mars lost its shield. It was left alone to face the sun's fury. The solar wind began to strip its atmosphere away into space, molecule by molecule. This process was slow but relentless, unfolding over tens of millions of years. As the atmosphere thinned, the pressure dropped. Water on the surface could no longer remain liquid. It began to vaporize and escape into space, while the remnants froze in the polar caps and beneath the surface, where we find them today. The planet began to dry out and freeze. The sun's ultraviolet radiation, no longer shielded by the ozone layer, sterilized the surface, killing all life. Mars was dying. If life ever existed there, it had a few options. The first was to perish along with its planet. The second was to go underground. Perhaps, somewhere deep beneath the surface, in subterranean reservoirs of briny water, protected from radiation by thick layers of soil, colonies of Martian microbes still exist. They could be the last remnants of a once thriving biosphere, and it is precisely them that our rovers are seeking, such as Perseverance and Curiosity. And there was a third option, flight. Those very asteroid impacts, bringing death and destruction, could, for some microorganisms, be their only chance for salvation. A ticket aboard the final ark, departing a dying planet. And if even one of these arks reached a young and hospitable Earth, then Martian life did not perish. It simply changed its address. It took root here, evolved, gave rise to an unimaginable diversity of forms, and eventually, after almost 4 billion years, one of its species, humankind, looked up at the night sky and saw a red light there, unaware that it was gazing upon the ruins of its ancient home. This idea flips everything on its head. If it's true, then we are all aliens on this planet. Studying Mars isn't just about exploring another world, it's the archaeology of our own, very deepest roots. When we search for life on Mars, we might not be looking for intelligent brethren, but our direct ancestors. Imagine that one day, a Mars rover drills a hole and finds a frozen bacterium in the subsurface ice. Scientists on Earth would analyze its genetic code and discover that it's based on the same DNA as all life on our planet. This would be the greatest discovery in the history of humankind. This would mean that life in the universe isn't a unique phenomenon, that it can travel between star systems. And that would mean that we are Martians. This also shifts our perspective on the so-called Fermi paradox, which asks, if the universe is full of planets, then where is everybody? Perhaps the answer is that life is a very fragile phenomenon. Planets capable of sustaining life may lose that ability over time. Mars is a clear example of this. It was alive, but it died. Perhaps every civilization in the universe encounters the Great Filter, a kind of barrier that prevents it from becoming interstellar. For Mars, its own geology became that filter. It simply proved to be too small to retain life for long. Earth was luckier. It turned out to be massive enough for its core to stay hot and its magnetic field strong. It sits at the ideal distance from the Sun. It has a large satellite, the Moon, which stabilizes its axis of rotation. Our planet managed to maintain conditions for life over billions of years, allowing evolution to progress from single-celled organisms to intelligent beings. We are the descendants of those who were fortunate twice. First, to escape a dying planet, and then to land on one that proved to be an ideal incubator. Today, we stand on the threshold of a new era. We are preparing to send humans to Mars. And in light of this hypothesis, such a mission takes on an entirely new, almost mystical meaning. This won't be just the conquest of a new world. This will be a return to the land of our ancestors, to try and understand what went wrong, and perhaps one day, with the help of our technology, to reignite the spark of life on that planet. To breathe a new atmosphere into it, to melt its ice, and to watch water flow once more through the dried riverbeds. Of course, this is just a hypothesis. Perhaps life originated right here on Earth, and Mars was always barren. Perhaps those bacteria-like structures in the meteorite are nothing more than a trick of nature. But until we find conclusive evidence, the idea of our Martian origin will remain one of the most thrilling and beautiful scientific theories. It reminds us that the universe is unified, that we are all made of stardust, and that the history of life might be far stranger and more captivating than we can possibly imagine. So the next time you look at the red planet, pause and reflect. Perhaps you're not looking at an alien world. Perhaps, deep within your DNA, in every cell of your body, lives the memory of a blue Martian sky and the sound of its ancient oceans. A memory of a home we left behind billions of years ago, and to which we now so desperately long to return. And perhaps, when the first human steps onto the surface of Mars, their first words shouldn't be about a giant leap for mankind, but about something simpler and more profound. We're home.